Welcome to Talk Tensors.
Today, we are looking at a paper that I think really represents the moment the dam broke.
We are indeed. We're covering a paper that future historians of, computer science, assuming that becomes a distinct job title, will probably look back on as the democratization moment of the whole large language model revolution.
That's a great way to put it.
We are, of course, unpacking LLaMA, Open and Efficient Foundation Language Models.
Published back in February 2023. And to really get why this paper is so important, you have to sort of mentally transport yourself back to that specific time.
It feels like a decade ago in AI years, doesn't it?
It really does. So early 2023, ChatGPT had just landed like a meteorite a few months before. The whole world was reeling from it.
Right. But if you were a researcher or a developer or even just a curious tinkerer, the landscape felt gated.
Completely gated. It felt like this amazing party was happening inside a fortress, and the rest of us were just standing outside of the moat, looking up at the walls.
The arms race was on, as they called it, but it was a race for giants. You had OpenAI with GPT-3, and all the early GPT-4 rumors were swirling.
And you had Google with PaLM and LaMDA, and the whole narrative, the dogma of the time was that if you wanted to play in this game, if you wanted state-of-the-art performance, you needed a massive, massive cluster of GPUs.
And a model with hundreds of billions of parameters.
It was the scaling law era.
Right. Based on that Kaplan et al. Paper from 2020, the logic was simple, right? To get smarter, you just get bigger.
More parameters, more power.
Yeah.
And bigger also meant proprietary. It meant closed doors. It meant if you didn't have, a few $1 million lying around for a compute budget, you were just a spectator.
Even on the sidelines watching.
And then this paper just drops. Out of nowhere, a team releases a whole set of models ranging from 7 billion all the way up to 65 billion parameters.
And they call it LLaMA.
And they essentially looked at the giants at the 175 billion parameter GPT-3 and said, we can match you. Actually, we can beat you.
And we can do it with a model that is a fraction of the size.
It was just this classic David versus Goliath setup. But the weapon wasn't a slingshot. It was efficiency.
Specifically, it was a total rejection of the idea that parameter count is the only metric that matters. It was a paradigm shift.
And it brings us to the thesis of this deep dive, which is really the thesis of the paper itself. You can build state-of-the-art models using only publicly available data.
And this is the kicker. You can run them on consumer hardware.
That's the key. That is the part that changed everything. Before this, the secret sauce was always some proprietary data mix or some secret architectural tweak.
The undocumented stuff.
Exactly. LLaMA basically proved that the recipe is out in the open if you just know how to cook it right.
All right, so let's get into that kitchen. But before we break down the model itself, we really need to talk about the theoretical shift that even allowed this to happen. You mentioned Kaplan and the bigger is better scaling laws, but then came the Chinchilla paper. And we need to unpack the difference here because it sets up literally everything that LLaMA did.
Yes, okay. The Chinchilla paper by Hoffman et al. In 2022 was the first major crack in the old dogma. Before Chinchilla, what researchers were doing was drastically undertraining their models.
What do you mean by undertraining?
Well, they would build a massive model, say 175 billion parameters like GPT-3, but they wouldn't feed it enough data to actually saturate those parameters.
So it's like buying a Ferrari and then only ever driving it in a 20-mile-per-hour school zone.
That's a perfect analogy.
Yep.
You have all this engine capacity, but you're not even close to using it.
So what did Chinchilla argue?
Chinchilla argued that for a given training budget, so for a fixed amount of money you're willing to spend on your compute, you should actually make the model smaller and train it on way, way more data.
It's all about the ratio.
It's all about the ratio. They found the optimal ratio was something like 20 tokens of data for every one parameter in the model. That was the sweet spot for training efficiency.
But LLaMA takes Chinchilla a step further, doesn't it? Because Chinchilla was still focused on the training budget, on the cost to build the thing.
This is the crucial distinction. This is the big idea in the LLaMA paper. Chinchilla optimized for the question, how much does it cost to build the model?
Just a one-time cost.
Right. But the LLaMA authors came along and said, wait a minute. We don't just build these things once and put them on a shelf. We have to run them.
Over and over and over again.
Billions of times. So they optimize for the inference budget.
Okay, I love the analogy we talked about for this. Let's use it. It's like buying a car. Chinchilla is focused on how much it costs to design and build the factory that makes the call.
A huge one-time capital expenditure.
But LLaMA is focused on the gas mileage, the miles per gallon.
Precisely. If you are going to deploy this model to millions of users, or if you want a researcher to be able to run it on a single GPU in their lab, the cost of running it, the inference cost, absolutely dominates the cost of training it.
I mean, think about it. Google runs inference billions of times a day. OpenAI is running it constantly for every single ChatGPT user. The training run, as expensive as it is, only happens once.
So if you optimize only for the training cost, you're being penny wise and pound foolish. You might save a little money on the compute cluster for that 1 month of training.
But then you pay for it forever. Every single time someone asks the chatbot a question, you're paying an inefficiency tax because your model is bloated.
Correct. So LLaMA's logic is, let's flip that. Let's spend way more money up front, burn way more gas building the factory. Let's train a smaller model for much, much longer than Chinchilla even recommends.
Because that smaller model is cheaper to run for the rest of its life.
Infinitely cheaper. So even if it costs you more to train it initially to get to that same level of intelligence, once it's trained, it's a 7 billion or 13 billion parameter model. It's lightweight. It just sips gas.
So they essentially overtrained these models by the traditional standards of the day.
Oh, significantly. So the Chinchilla scaling laws would suggest that for a 7 billion parameter model, you should train it on about 200 billion tokens. That's the optimal stopping point if you're optimizing for training cost.
And what did the LLaMA team do?
They said, ignore that. They trained their 7B model on 1.4 trillion tokens.
Wow. That's 7 times the recommended amount.
It's a massive discrepancy. It's like studying for an exam for 7 years instead of the recommended 1 year.
And the result is a model that is just incredibly dense with information for its size. It's like compressed intelligence.
That's a great way to think about it.
Okay, so let's talk about that information. The mission here wasn't just about efficiency, it was also about openness. And one of the boldest choices in this whole paper is the constraint they put on themselves regarding the data.
The public-only rule.
Explain that.
No proprietary datasets, no internal company emails, no undocumented heaps of text that other companies were using but not telling anyone about. Everything had to be publicly accessible.
Why does that matter so much to the scientific community? I mean, isn't data just data at the end of the day?
It matters for reproducibility. It's the bedrock of science. Think about the replication crisis in psychology or really any scientific field where the raw data isn't available. AI was heading down that exact same path.
How so?
Well, if I publish a paper saying, I built this amazing model that speaks perfect French, but I trained it on a secret database of French literature that you can't access.
Then I can't verify your work. I can't replicate it.
Exactly. It's not science anymore. It's alchemy. It becomes a kind of trust me, bro citation.
Right. And you also can't audit it for things like bias.
That's the other huge piece. If a model has a weird worldview or says something toxic, you need to be able to look at the training data to see where that came from. So by using only publicly available sources, Common Crawl, Wikipedia, GitHub, the LLaMA authors made their work falsifiable. They made it reproducible.
They gave us the recipe, not just the finished meal.
The perfect summary.
So let's look at the ingredients list for this recipe. They've fed this thing 1.4 trillion tokens. That is a number that is just hard to wrap your head around. What is actually in there?
So the backbone, as with pretty much all LLMs then and now, is Common Crawl. That makes up about 67% of the total training data.
And for those who don't know, I mean, we all know Common Crawl is the default starting point, but we also know it's like a 90% noise.
It's the internet. It's navigation bars. It's cookie consent pop-ups. It's spam. It's low-quality rants and comment sections. It is the internet, warts and all.
So the secret then isn't just using Common Crawl, it's how you clean it.
It's all in the cleaning. The paper details this CCNet pipeline they used. They go through this massive deduplication process to remove duplicate pages. They use fast text classifiers to filter out non-English pages. They even use n-gram models to filter out what they call low-quality content.
But my favorite detail is the clever trick they use with Wikipedia as a filter.
Oh, the reference trick.
Yes, it's such a brilliant heuristic.
It really is.
Yeah.
So they trained a simple linear model to classify pages.
Yeah.
And the rule was, if a web page is cited as a reference in a Wikipedia article, it's probably high-quality text.
Because a human editor at some point decided it was worth linking to.
Precisely. If it looks like some random spam site, it gets tossed.
Mm-hmm.
So they're essentially using the collective human curation of Wikipedia to filter the absolute chaos of the open web.
That is so smart. It's using established anchors of truth to clean the noise. Okay, so Common Crawl is the bulk. What else is in the mix?
Next up, you have C4, which is the colossal clean-crawled corpus. That's another 15%. It's a standard, already cleaner version of the web. But then we start getting to the really high-value nutrients. GitHub. That's 4.5% of the data. And this is critical. They filtered for public code under permissive open licenses, Apache, BSD, MIT, and so on.
Now, obviously, this helps the model learn to write code, but I've heard researchers argue that training on code helps the model do a lot more than just write code. Does learning Python really help a model write a better poem?
I would say absolutely. Think about what code is at a fundamental level. Code is logic. Code is structured reasoning. It's if this, then that. It's while X is true, do Y. It's define function A and then call it later in context B.
So you're not just teaching it syntax.
Not at all. You are teaching it how to structure a complex argument, how to follow a chain of logic without breaking it, and how to handle rigid hierarchical structures. It boosts reasoning capabilities across the board, even in what we think of as pure natural language tasks.
That makes total sense. It's like learning Latin to understand English grammar better. You're learning the underlying structure of thought.
A perfect analogy. Okay, then they added Wikipedia itself, about 4.5%. This is the raw knowledge base. It covers 20 different languages, but they stripped out all the HTML boilerplate, the hyperlinks, the little edit buttons.
Just the pure informational text.
Exactly. And then books.
Gutenberg and Books 3.
Right. Another 4.5%. And this is crucial for what we call long context. The web is all short attention span. Tweets, blog posts, forum comments.
Right.
Books require the model to track a narrative or a character or a complex argument over hundreds of pages. It teaches coherence. If you want a model that can write a decent short story, it needs to have read a few novels.
And finally, the really hard sciences.
ArtSph and Stack Exchange. ArtSph is about 2.5%. That's scientific papers, mostly in physics, math, computer science. And Stack Exchange is 2%, which is just this treasure trove of high-quality Q&A on everything from chemistry to programming.
I noticed a specific detail about how they processed the ArtSph data. They removed the bibliographies.
And the comments in the source files. They wanted the meat of the paper, the reasoning, the equations. They actually processed the raw LaTeX files to make sure the math was represented correctly for the model.
Speaking of math, that brings us to a fascinating technical detail in the tokenization section. It's a tiny detail, but the paper makes a point of highlighting it. They split all numbers into individual digits.
Yes. This is such a clever move. It solves a classic gotcha in older language models. So typically a tokenizer, which is the thing that chops text up into numerical tokens the model can actually read, uses the method called byte pair encoding, or BPE.
And BPE tries to group common characters together. So the year 1995 might become a single token.
Exactly. The model sees 1995 as a single unique concept, just like the word apple or the word river.
And that's a problem for doing math.
It's a huge problem. If the model sees 1995 as one indivisible symbol, it doesn't inherently understand that it's made of a 1, a 9, a 9, and a 5. It doesn't inherently get that 1996 is just 1995 plus 1.
To the model, they're just two different vectors, as distinct as cat and dog.
Precisely. So by forcing the tokenizer to split all numbers into their individual digits, what happens?
The model now sees 1, 9, 9, 5.
Right. And over 1 trillion tokens of data, it learns the place value system. It learns what happens when you add 1 to the last digit, that the 5 becomes a 6. It dramatically improves its mathematical reasoning capabilities just by changing how you feed the text in. It
stops memorizing answers and actually starts calculating them.
It starts to learn the algorithm of arithmetic.
It's amazing how these seemingly small pre-processing decisions have such massive downstream effects. We always focus on the neural net layers and the architecture.
But the tokenizer is the mouth of the beast. If you can't chew the food properly, you can't digest it. The data pipeline is so often where the battle is really won or lost.
Well, let's look at the architecture anyway, because they call this a transformer, but it's not exactly the vanilla transformer from the original 2017 Attention is All You Need paper. It's a bit of a best-of-breed Frankenstein monster.
It is. They didn't go out and invent some radical new architecture here. They were very practical. They looked at what was working in GPT-3, what worked in PaLM, and what worked in GPT-Neo, and they just combined the best parts.
So it's a standard transformer at its core, but with 3 very specific, high-impact, modern modifications.
That's right.
Let's walk through these, because for our listeners who actually build these things, these details really matter. So modification number 1, pre-normalization using RMS norm.
This was inspired by GPT-3. So in the original transformer, you normalize the data, which basically means you standardize the numbers so they don't get too big or too small after it goes through a layer like the attention layer. That's called post-norm.
And LLaMA does it before, pre-norm.
Right. LLaMA normalizes the input before it enters each sublayer.
Okay, in plain English, what does that actually do for the training run? Why is that better?
It's all about stability. Training these massive models is like trying to balance a pencil on its tip while you're riding a roller coaster. It's incredibly unstable. The gradients, which are the signals telling the model how to learn, can easily explode and get too big or vanish and get too small.
And the whole training run just crashes.
The whole thing crashes and you've just wasted $1 million. Pre-normalization keeps the signal propagation much cleaner and more stable as it goes through the network. It allows you to train deeper networks without them diverging.
Got it. So it's basically the suspension system of the car. It smooths out the ride. Okay, modification number 2. The SWIGGLEU activation function.
This one is just fun to say. SWIGGLEU. It's inspired by Google's PaLM model.
And it replaces the standard activation function, which is usually something called ReLU, right?
Correct. Most neural nets for a long time used ReLU, which stands for rectified linear unit. It's a very simple function. If a number is positive, you keep it. If it's negative, you just make it 0.
It's a very harsh on-off switch.
A very simple gate. SWIGGLEU is what's called a gated linear unit, and it's much smoother. Think of ReLU as a light switch that is either on or off. SWIGGLEU is more like a dimmer switch that also has a complex little logic gate attached to it that helps it decide how much light to let through.
So it allows the model to control the flow of information much more subtly.
Much more subtly. It technically requires a bit more compute. There are more matrix multiplications involved, but it consistently yields better performance for the same parameter count. It just seems to capture more nuance in the data.
Okay, now for the big one. This feels like the most important of the 3. Modification number 3, rotary embeddings, or ROP. This seems to be the industry standard now, but LLaMA was one of the big models to really popularize it.
Yes, ROP. This is all about solving the position problem in a transformer.
Right, because a transformer, by design, processes all the words in a sentence at the same time in parallel. So it doesn't inherently know that the word "the" came before the word "cat." You have to explicitly tell it the order of the words.
Exactly. And traditional models used what are called absolute position embeddings. They would literally just add a vector to each word's embedding that says, you are token #5, you are token #6, you are token #7.
What's the problem with that?
The problem is, what happens if you train your model only on sentences up to 2,000 words long, and then at inference time, you try to give it a 4,000-word document?
It freaks out because it has never seen token #3000 before.
It falls off the edge of its own map. It doesn't know how to generalize to longer sequences.
So how does ROP fix this? The paper talks about rotations, which sounds complicated.
It's a really elegant idea. So instead of encoding an absolute position, ROP-E encodes the relative position of tokens. Imagine a clock face. Standard embeddings are like putting a sticky note on the minute hand that says, this is minute 5.
Okay.
ROP-E is different. It defines the relationship by the angle between the hands. So whether the hands are at 12:00 and 12.15 or at 6.00 and 6.15, the relationship between them is identical. It's 90 degrees.
Ah, I see.
ROP-E encodes the position of words as rotations in a high-dimensional vector space. So the model learns things like the subject is usually near the verb, regardless of whether that happens at the start of a book or at the very end.
So for dog bites man versus man bites dog, the model understands the crucial difference based on the rotational distance between the words, not just their absolute place in the sentence.
Precisely. And because it's based on these rotational properties, it generalizes much, much better to sequence lengths that are longer than what it was trained on. This is why LLaMA models and their descendants are so good at being extended to very long contexts later on.
So we have the data clean, code heavy, digit split, and we have the architecture prenorm, SWIGGLEU, and ROPE. Now we need to actually cook this thing. Let's talk training and optimization.
This is where we get into the heavy iron. So they used a cluster of 2048 NVIDIA A100 GPUs. And these were the 80 GB RAM versions, the absolute Ferraris of the GPU world at that time.
And even with over 2,000 of them, it wasn't exactly an instant process.
Not at all. To train the big one, the 65 billion parameter model on the full 1.4 trillion tokens took 21 days.
3 solid weeks of continuous full throttle compute.
Just imagine trying to keep a cluster of 2,000 machines running perfectly for 3 weeks straight. It's an incredible engineering feat in itself.
And they had to use some clever software tricks to make it all fit and run efficiently. The paper mentions using an efficient implementation of causal multi-head attention via a library called XFormers.
Right. This is a classic efficiency hack. In a standard, naive implementation of attention, you compute and store this massive matrix of attention scores, how much every single word in the sequence should pay attention to every other word.
But in a language model, a word can only look at the words that came before it. It can't look into the future.
Exactly. That's the causal part. So half of that giant attention matrix is masked out. It's filled with useless zeros that you're not allowed to look at.
But you're still using memory and compute to calculate and store those zeros.
In the naive version, yes. The XFormers library is smart. It has an implementation that is clever enough not to compute or store the parts of the matrix that are going to be masked out anyway. It saves a ton of memory and time.
They also mentioned something called checkpointing. This is a concept that always confuses me because it sounds like you're saving your game, but it's actually about memory management, right?
It's more formally called gradient checkpointing, and it's a trade-off. So normally, during the forward pass, when the data is flowing through the model, you save all the intermediate results, all the activations at every layer.
So you can use them later in the backward pass when the model is actually learning.
Right. But storing all of those activations takes up a huge amount of memory. You run out of VRAM very quickly on the GPU.
So checkpointing means you don't save everything.
Exactly. To save RAM, you strategically throw some of those intermediate results away. Then during the backward pass, when you get to a point where you need one of those numbers you discarded, you quickly recalculate it from the previous checkpointed step.
So you're literally doing the math twice for some parts of the model.
Yes. You are trading compute, which is time for memory, which is VRAM. You accept that the training run will be slightly slower because of this recalculation. But in exchange, you can fit a much bigger batch size or even a bigger model onto your GPUs. It's a classic engineering compromise.
All right, let's get to the main event, the part everyone was waiting for, the results. This is the David versus Goliath moment we promised at the start.
And it really was. The headline statistic, the one that sent shockwaves through the entire industry, was this. LLaMA 13B outperforms GPT-3 on most benchmarks.
Okay, let's just pause on that for a second. GPT-3 is 175 billion parameters. LLaMA 13B is 13 billion. It is less than 1/10 the size.
Less than 10% of the size, and it wins. This was the aha moment for the whole field. It was the definitive proof that GPT-3 was massively, massively undertrained. It was bloated.
And it proved you could get that same level of intelligence on a single consumer GPU. I mean, a high-end gaming card like an RTX 3090 or 4090 could suddenly run a model that was as smart as what we previously thought required a supercomputer.
And that changes everything. That opens the door for every researcher, every startup, every hobbyist. Suddenly, you can run a GPT-3 class brain on your home computer. You don't need access to a multi-million-dollar data center anymore.
That is the democratization. But they didn't stop there, right? They also trained the big one, the 65 billion parameter model.
It's heavyweight contender. And this one went toe-to-toe with the absolute best, most powerful models in the world at the time. DeepMind's Chinchilla 70B and Google's Pelham 540B.
Pelham 540B, that's Google's Leviathan, over 500 billion parameters, just a monster.
And LLaMA 65B, at a fraction of the size, is competitive with it. It actually beats Chinchilla on almost all the common sense reasoning benchmarks.
What are those exactly?
Things with names like BoolQ, PIQA, HellaSwag. These are tests that ask basic physical and social logic questions. You know, if I drop a bowling ball on a glass window, which one is more likely to break?
And LLaMA was better at that.
Consistently better, even at the 13B size against GPT-3.
What about closed book QA? This is like a trivia night where the model can't use Google.
The benchmarks are natural questions and trivia QA. And here, LLaMA 65B achieves state-of-the-art results in both zero-shot and few-shot settings. It was answering questions about facts, history, science, and pop culture better than models that were 10 times its size.
There is one result in the paper that really jumped out at me because it seems so counterintuitive. It's in mathematical reasoning. The benchmark is called GSM-8K.
Ah, yes, GSM-8K. This benchmark involves multi-step grade school math word problems, things that require a few steps of logic and arithmetic to solve.
And LLaMA 65B scores 50.9%. Now, that might not sound super high compared to today's models, but here's the kicker. It outperformed a model called Minerva 62B.
And Minerva was a model that was specifically fine-tuned on math data, wasn't it?
Yes. Minerva is a version of Pelham that was specialized just for math and science. LLaMA was not fine-tuned for math at all. It just learned it from the general pre-training mix.
Probably thanks to that digit-splitting tokenization trick in all the scientific papers from ArtCiv in the dataset.
It beat a specialist at its own game just by being a better, more efficient generalist. That's incredible.
Same story with code generation.
A very similar story. On human evil and MBPP, which are the standard coding benchmarks, LLaMA beats other generalist models like LaMDA and PaulM. Now, to be fair, it doesn't beat the dedicated code-specific models like PaulM Coder.
But for a general-purpose model that wasn't explicitly told your job is to be a coder, it is incredibly strong.
However, we have to be fair. It wasn't a clean sweep across the board. There was one notable weak spot.
MMLU, massive multitask language understanding. This is a beast of a benchmark. It covers 57 different subjects: humanities, STEM, U.S. history, professional law, medicine. It requires very deep, specialized knowledge.
And LLaMA 65B scored 63.4%. Chinchilla scored 67.5%, and PaulM 540B scored 69.3%. So it did lag behind the giants here. Why? Is it just because it's a smaller model?
The authors speculate in the paper, and I think they're right, that it comes down to the amount of book data. LLaMA's training data only had about 177 gigabytes of book data.
And the others?
The models it's being compared to, like Gopher and Chinchilla, used up to 2 terabytes of books in their training mix.
Whoa. Okay, that is a huge difference, an order of magnitude more.
It is. And books contain that deep, dense, academic, nuanced knowledge that you just don't find on Reddit or in a typical Common Crawl scrape. So you could say LLaMA was incredibly street smart because of all the web data, but it lacks some of the deep book smarts of the absolute largest models.
It's interesting, though, they note in a footnote that a very brief instruction fine-tuning version they called LLaMA jumped the MMU score all the way up to 68.9%.
Which means the knowledge was arguably in there somewhere. It was latent. The pre-training laid the foundation, but the lack of specific instruction tuning was holding it back slightly on those very complex academic-style tasks.
Now, we can't do a deep dive on these foundational models without talking about the dark side. The paper includes a whole section on the evaluation of bias, toxicity, and misinformation. They hold up a mirror to their own creation.
And the reflection isn't always pretty. They use a benchmark called real toxicity prompts.
Yeah.
And they found something that is disturbing, but also pretty consistent with other research at the time.
Which is?
Toxicity increases with model size.
Wait, hold on. The smarter the model gets, the more toxic it is. That feels completely backwards. Shouldn't intelligence correlate with, being better?
But not for a large language model.
Yeah.
You have to remember what an LLM is. It's a mimic. It's a machine for modeling the statistical distribution of the data it sees.
Okay.
The 65B model is a better mimic, a higher fidelity mirror than the 7B model. And since the web, particularly Common Crawl, contains a lot of hate speech, insults, and general toxicity, a better model is simply better at generating that filth when it's prompted to.
It's good at being bad.
It's excellent at being bad. It's not evil. It's just a high-fidelity reflection of humanity's worst online behavior. A smaller, dumber model might get confused and output nonsense. The big, smart model knows exactly how to finish a toxic sentence because it has seen millions of examples of how to do it.
They also tested for gender bias using a benchmark called WinoGender.
Yes, and this was fascinating. They found that the model is actually significantly better at handling gender-neutral pronouns like their and them than her or him. But the real bias shows up in what you might call the gotcha cases.
Give us an example.
Okay, so take a sentence like, the nurse notified the patient that his shift would be ending soon. The model's task is to figure out who his refers to.
Grammatically, his shift should refer to the nurse.
Correct. But because the model has learned from the training data, the strong societal stereotype that nurse, female, it gets confused. It struggles when the pronoun in the sentence doesn't match the stereotype of the occupation.
It leans on the statistical bias from the data over the actual grammatical evidence in the sentence.
Precisely. It's capturing the bias of our society, which is embedded in the text we've written, rather than reasoning purely from the logical structure of the sentence in front of it.
And they found a similar issue with religion.
On the Crosspairs benchmark, yes. LLaMA showed a notably high bias in the religion category, even higher than other large models like OPT 175B. And again, this likely comes down to the unfiltered nature of Common Crawl, which is full of, heated and biased internet debates about religion.
The clean datasets like Wikipedia couldn't fully dilute the messy reality of the internet.
Exactly.
And finally, on the responsibility front, the carbon footprint. We touched on the 2,000 GPUs for 3 weeks. What was the final environmental bill for this project?
They estimated the total emissions at around 1,015 tons of CO2 equivalent. To put that in context for you, the Bloom model was around 27 tons. The OPT model was 82 tons.
Yeah, LLaMA was dirty. It was a heavy footprint.
It was heavy, and that's a direct result of the core philosophy, training for way longer. That 1.4 trillion tokens just takes a lot of energy to process. But, and this is the author's rebuttal in the paper, which I find very compelling, they argued that by releasing these models openly, they actually save carbon in the long run.
Explain that logic.
Because now, thousands of researchers and developers around the world don't have to train their own foundational models from scratch. They can just download and fine-tune LLaMA.
It's a high upfront cost to create a public good that prevents thousands of redundant, smaller training runs.
Exactly. You amortize the carbon cost across the entire research community. If 10 different university labs download LLaMA, instead of each training their own OPT-sized model, you've just saved thousands of tons of CO2.
So we have the paper, the stats, the good and the bad. But the real story of LLaMA, the lasting impact, is what happened after it was published.
Its legacy. This paper single-handedly triggered the open source AI explosion. Before LLaMA, if you wanted to work with a powerful LLM, you were calling an API from OpenAI or Google. You were renting intelligence.
You were totally dependent on their uptime, their censorship policies, their pricing. You were a tenant.
And after LLaMA was released and subsequently leaked, people started quantizing it to run on MacBooks. They built llama.cpp to run it on a CPU. They fine-tuned it on instructions to create amazing new models like Alpaca and Vicuna. It just sparked this Cambrian explosion of local OpenAI development.
It proved you don't need a moat. It proved that efficiency can beat pure brute force size. And it cemented this overtraining idea that training smaller models on massive amounts of data is the correct path for the future of AI deployment.
We're still living in the LLaMA era today.
Yeah.
Every single time you see a new small language model or an SLM that can run on your phone, it owes a direct intellectual debt to this paper.
It really was the moment the moat around the castle filled up with sand. Anyone could just walk right across.
Precisely.
All right, that brings us to the end of our main analysis. We're not done yet. It is time for
Novel notions.
This is the segment where we take the core logic of the paper, we push it right off a cliff, and we see if it flies. For entertainment purposes only, of course.
The standard disclaimer is now firmly applied.
I'll go first. I'm calling this one the eternal student hypothesis, or maybe the 1B parameter superbrain.
Okay, I like the sound of that.
So the paper showed that the LLaMA Mass 7B model was still improving after 1 trillion tokens. The loss curve was still going down. It hadn't flatlined.
Right. It hadn't saturated its capacity to learn yet.
So the core logic of the paper is training is a one-time cost. Inference is forever. My notion is, what if we took that to its absolute logical extreme? What if we built a tiny model, say 1 billion parameters, something that could easily run on a smartwatch or a smart thermostat?
The Ant-Man of models.
Exactly, the Ant-Man model. But instead of training it on 1 trillion tokens, we train it on 100 trillion tokens. We just run the training for a full year on a massive cluster. We spend $100 million training this model that is absolutely tiny.
A lossless training run. You refuse to add more parameters, but you refuse to stop feeding it data until the loss curve is perfectly mathematically flat.
Yes. What happens? Does a 1B model eventually hit some kind of hard wall of intelligence it can't pass? Or, if you just show it enough examples, does it eventually memorize and compress enough patterns to become as smart as GPT-4, but in a package that costs fractions of a penny to run?
It's a fascinating question of information compression. Can 1 billion parameters physically hold that much complexity and nuance? The LLaMA paper suggests we haven't found that limit yet, and if this works, you completely revolutionize edge computing. You would have super intelligence running locally on your toaster.
That's the dream. Your toaster arguing with you about the optimal Browning setting based on first principles thermodynamics.
Or quoting philosophy at you while it does it. My notion takes a different angle. I'm looking at the bias section of the paper.
Okay, let's hear it.
I'm calling it the siloed bias detector.
Ominous. I like it.
So the paper explicitly noted that specific types of biases came from specific datasets. The religion bias probably came from Common Crawl. The male nurse gender bias comes from the statistical occurrences in all text.
Right. Garbage in, garbage out.
But currently, our approach is to mix all the garbage together into one giant homogeneous smoothie and feed it to the model. Then we try to filter the toxic output at the end. My idea is, don't mix the smoothie in the first place.
Keep the ingredients separate.
Exactly. Instead of one giant model, you train 5 separate LLaMA 7B models. One of them sees only Wikipedia. Another one sees only Reddit and Stack Exchange. A third one sees only archived scientific papers. A fourth sees only carefully curated literature and books.
A council of experts.
A council of experts. So when a prompt comes in, you send it to all 5 models in parallel. Let's say the prompt is a controversial one. The Reddit trained model might give a toxic, biased, sarcastic answer. The Wiki trained model will give a neutral, factual, encyclopedic answer. And the ArcDef model gives a highly technical, jargon-filled answer.
And because you know which model produced which output, you can mathematically isolate the bias.
You can perform vector subtraction in the embedding space. You can treat toxicity or bias not as a bug to be stamped out, but as a known feature of the Reddit model. So you can literally subtract the Reddit vector from the final combined response to debias it.
You modularize the bias so you can turn the volume knob up or down on it as needed?
Precisely. Instead of a single black box that is vaguely racist some of the time for unknown reasons, you have a control panel. Turn down the Reddit knob, turn up the science knob.
I love that. It turns the alignment problem into an engineering control problem.
Which is usually how we actually solve things in the real world.
Well, there you have it. From the 7 billion parameters that shook the world to a council of experts living inside your toaster.
It's been a journey.
This has been a deep dive into the LLaMA paper. The moment the closed doors of AI flew open and efficiency became the new king. Thanks for listening to Talk Tensors.
See you next time.